Hello everyone, my name is Rosu, and together with my colleagues at the University of Bonn, we developed LatticeNet, a network for fast point cloud segmentation using permutohedral lattices. Semantic segmentation of 2D images has shown great success with novel deep learning methods. However, the projective nature of an image naturally discards information about the 3D scene, for example depth and proximity between objects. A better idea would be to use the 3D data directly, for example point cloud recorded by LiDAR or Kinect-like sensors. However, the question arises, how can we efficiently perform semantic segmentation on a point cloud? Here we propose LatticeNet, a method that embeds the point cloud into a sparse permutohedral lattice and defines the convolutions in lattice space. The permutohedral lattice has several advantages as a representation. First, it has sparse storage, which means the lattice is only allocated where the surface of interest exists. Secondly, it has linear growth with respect to dimensionality, compared to the exponential growth of a cubical lattice. Thirdly, it also has less quantization issues due to the fact that the signal is interpolated into the lattice. In our method, we take as input a raw point cloud and embed it into a sparse lattice. Afterwards, together with upsampling and downsampling operations, we get a more and more global context. Finally, the features of the lattice are interpolated back onto the point cloud for the final prediction. We extend the current approaches with novel operations. Previous work would map the features of the points onto the lattice using a splatting operation. However, this would cause a loss of information as the features of the points would merge together. Here we propose a distribute operation, which keeps track of the contributions of the points and causes no loss of information. Afterwards, the features are embedded into a higher dimensional space using a point net architecture. Context aggregation is performed by upsampling and downsampling operations. And the advantage is that these operations perform only on the lattice and are therefore independent of the size of the input point cloud, gaining therefore memory efficiency and speed. Finally, the features of the lattice are mapped back onto the points using ascending interpolation. However, this is a fixed function, which means it has no learnable parameters. Here we define the from slice, a method which first gathers the features of the lattice and then regresses new Baran-Searchy coordinates. This has the advantage that it's a learned operation, which allows the network to learn a better interpolation scheme, further reducing quantization issues. We model architecture as a UNet model, together with skip connections and vertical concatenation. All modules in the network are learnable. We evaluate our results on the ShapeNet, ScanNet, and Semantic Kitty datasets. We show competitive results in ShapeNet and the ScanNet dataset. In the case of Semantic Kitty, we establish a new state-of-the-art with 52.9 intersection over union. Compared to SplatNet, which is another work that uses the permutohedral lattice, we have a significant improvement with respect to the intersection over union. With respect to performance, we improve by almost 2.6 the timings on the ShapeNet dataset and also improve the memory usage. In the case of Semantic Kitty, which contains larger point clouds, the improvement with respect to time and memory usage is even more apparent. With respect to ScanNet, which is the biggest dataset with the largest point clouds, the work of SplatNet couldn't run due to memory constraints. However, our approach can still run with enough memory to spare. Here we show results from the ScanNet datasets, where we segment large, room-sized point clouds into 20 classes. Additionally, we also use the network pre-trained on ScanNet to segment our own recorded data, and we show that the network generalizes well to new settings. Here we show an example of an input point cloud which is devoid of color, which means the only feature used by the network is the geometric structure. Here we show results on the Semantic Kitty dataset, which consists of sequential LiDAR scans, and we segment them into 19 classes. We propose a fast network for semantic segmentation of raw point clouds, and we define novel operations on the permutohedral lattice that significantly improve segmentation results. We also make the code available for everyone to try. Thank you for watching.